I'm oral historian Mike Chappell. Today, June 15th, 2013, I'm interviewing Dr. Hector DeLuca for the Endocrine Society at its annual meeting being held at the Moscone Center in San Francisco.
I decided I was going to find out what I could about how vitamin D works. So being trained in organic chemistry, I decided I'm going to make vitamin D labeled so highly labeled that I can follow a true physiologic dose. And that's when I started on the course of, so the first thing I did was to try to find out, does vitamin D get changed during the course of its action? So we gave radio-labeled vitamin D and then extracted the tissues and chromatographed the extracts. And sure enough, vitamin D disappeared and the radioactivity appeared in a substance that wasn't vitamin D anymore. And so right away I got the collaboration of Dr. Heinrich Schnoes, who was a mass spectrometer expert. And mass spectrometry had just come into its being for identification of structure. And we identified 25-hydroxy-D in the blood of pigs given high doses of vitamin D. 1968, we synthesized it to prove its structure.
Now this was where the radioactivity ended up?
Yeah, it ended up, well, that was the first place that we found it. The major peak was this peak 4, we called it. And we could find it in rats, but it was impure. You couldn't determine the structure. So what we did was go to a bigger animal, give higher doses of vitamin D, including taking a small pig and giving it radio label so we could follow it. And so we had the extract of 4 pigs, all the blood of 4 pigs, the blood serum, and we added the blood serum of this little pig that had gotten radio-labeled vitamin D, and now we could follow the label. Mm-hmm. And we went through about 4 chromatographic steps, and finally the last one gave us a pure vitamin D absorption band, and we did the mass spectrometer on it, and we could determine that it was 25-hydroxy-D. And then we synthesized it and proved it in 1969.
Now, how did you feel at that point when you had that?
Well, we thought it was the active form at first, but you know what? The fact you had a hydroxyl on the 25 position means you could label it really easily. You could do a Grignard on an aldehyde or on an ester and put 6 tritiums. So we did that, and when we gave that, it disappeared before you could get a biological response.
You had no idea that was going to happen?
No. So then we thought, and then we isolated 3 peaks in blood, and I thought, this could be endless. We better go to a target tissue. So we gave radio-label to 1,600 chickens, and we took the intestines, which we knew was a target. We started with vitamin D deficient, so we wouldn't be, so we would know the specific activity of the radio-label, and sure enough, we found this compound. And we went through 8 chromatographic steps. It still wasn't pure enough to get a mass spec on it. And finally, I found there's the 25 positions was called a tertiary hydroxyl. And so it's hard to esterify, but it's even harder to pull the ester group off. So what we did was make a trimethyl silyl derivative of all the hydroxyl groups. That means the 3 and the 1 as well on the A ring, and the 25 on the was labeled, and then we, with mild conditions, hydrolyzed off the TMS on the A ring, which left the TMS on the side chain. But the contaminating lipid obviously didn't have a tertiary hydroxyl, so we could pull it apart chromatographically. We got pure stuff, and we determined the structure. So that was 1971.
And what was the pure stuff?
125 dihydroxy vitamin D. But we couldn't tell whether the configuration was alpha or beta, so we then went ahead and synthesized it and proved that it was the 1-alpha.